really the standard piece which we have in gauge theory, R alpha beta, which R alpha beta. Which just can be rewritten like in the Maxwell case as an exact form. I mean, you can really just note the CRR minus, it turns out to be gamma alpha beta. I hope I get all signs right, but in case I don't, I'm sure that Weichen will correct me. So plus 1/3 gamma alpha beta, which gamma beta gamma, which gamma gamma alpha. So this is the famous Chern-Simons term in gauge theory, and we have it also here. It's this form R, which it's also, I mean, the derivative is just R, which R. You can easily. And the twisted Euler form. Now the point is that in gauge theories we can not only build the Hodge dual but also the dual with respect to these indices alpha beta. We call this, because these are V algebra valued indices, we call it the V dual. So we define the Euler form. This is the standard Euler topological form, which is known from differential geometry, which is parity conserving, P plus, and which is filled with R and R with the Lie dual. Let me define the Lie dual for you. The Lie dual of a form, so R alpha beta, the Lie dual R, Lie dual, which I take such a star, alpha beta. It's just a dual with respect to these indices is by definition 1/2 times eta mu alpha beta times right? It's just an ordinary dual with respect to these two indices. And so this is the E C R R Lie dual plus, because it's positive parity, it's R alpha beta, which R Lie dual alpha beta. Okay, so we have two boundary terms, and we have to add these two boundary terms with two factors in order to compensate for other. So we have V strong gravity, the whole strong gravity piece is V strong plus V strong minus plus F2 over rho, Rabi constant, times the boundary term RR, this is the Poincaré term, RR, which is minus, plus F3 over rho times the boundary term from the Euler. Euler is parity positive, R V star. So this is the whole strong gravity Lagrangian. So now we can finally collect our whole Lagrangian, which depends on the strong plus on the weak piece. So the whole gravity Lagrangian of the quadratic Poincaré gauge theory, small q Pg, is V weak plus V minus weak plus V strong plus V minus strong plus F1 over kappa times the boundary term for the torsion, B minus torsion, plus F2 over rho times B minus R plus F3 over rho B minus R Hodge star plus F3 B plus no, the Hodge star comes to the last term, sorry. This is B minus R, this is correct, and this is B plus R Hodge star. So this is our total Lagrangian. Now the last thing is to express the Hodge star in the Euler star in the Hodge star in order to eliminate this Hodge star, this Lie star. So we have the Lie star, this is this one, Lie star, and we have the Hodge star which enters here. T star in all quadratic pieces which are parity even, you have here the Hodge star. Now we have a computer program which expresses the Lie star in the Hodge stars. This is also, these formulas are were not known before. We first complete them as far as I know there. So if you have the irreducible piece number capital I of R nu which, and now we the Hodge the Lie star, the piece R I times R Lie star, parenthesis, nu. Now the calculation gives that this is plus or minus the same for the Hodge star. I R nu which the Hodge star of R nu, and the plus is for I equals 1, 3, 5, 6, 1, 3, 5, 6, and the minus for I equals 2 and 4. So you can always transform the Lie star into a Hodge star up to a sign. And the sign you have to try to decide which piece it is. And if you substitute that into the Euler form, this is the Euler form, E plus R Lie star, then you get 1/2, and now we have the Hodge star, parenthesis R alpha beta, which Hodge star R alpha beta minus 2 times 4 R alpha beta, which Hodge star 4 alpha R alpha beta, and then one term is R minus 2 times the second piece R alpha beta, which alpha beta is the second piece. No, the sum. There must be a sum. parentheses. It's all multiplied by a factor 1/2. And the same way, you can decompose the quantary eigenform. Incidentally, you can specialize this for Riemannian spaces, and also in Riemannian spaces, both terms contribute. What is called the Euler form, it's usually called, in Riemannian case, the Gauss-Bonnet theorem, where you relate, this is the Ricci, the symmetric trace-free part of the Ricci, and here this is the pair form which vanishes in the Riemannian space. So in the Riemannian space you have only the total R piece and the Ricci piece which enter, and you can, of course, you can here have the Weil piece minus the Ricci piece plus the scalar piece. So you have two terms left over, and this is usually is called in Einstein's theory the Gauss-Bonnet term, because it is Euler topologically invariant, is related to the Gauss-Bonnet invariant, Gauss-Bonnet. For Riemannian space. So this is a generalization for Riemann-Cartan space. So what we have done is to generalize the Gauss-Bonnet theorem of the Riemannian space to a Riemann-Cartan space, and also the Poincaré eigenform. And these are very important topological quantities. Okay, so now I can write down the final Lagrangian. I do not rewrite now this Gauss-Bonnet term. So we have, for strong gravity, we have then all those constants which we discussed here, but we can compensate two constants here by these terms. And for weak gravity, we can compensate one constant. And so what is left over is then 8 terms for parity for the strong piece, and I write this down now. So the final Lagrangian then, V quadratic by Gravitation theory, and I hope that you now understand the motivation for each of these pieces. 2 kappa bracket. Now we have here A0 times the Riemann, the Einstein-Cartan piece. I write it as scalar, minus 2 times lambda 0, the cosmological constant, plus Arbero im Ricci parameter, P0 times x, this is a pseudoscalar which we had introduced, parentheses times the 4 form. So this piece is often called in the literature the Holst piece. This one is the Arbero im Ricci parameter, which is not historically correct. And then we have the torsion square pieces, which I can put up here, for instance, plus A2 over 3 times the vector piece of the torsion, V, which Hodge dual of V plus minus V is a one form. We defined it, the vector piece of the torsion, minus A3 over 3 times the axial torsion A, which star A, and then we have one mixed piece minus parity odd sigma 2 over 3 times vector piece which Hodge of the axial vector piece, so it's parity odd. And we have here A1 times the tensor piece of the torsion, P1, P alpha, which P alpha. That's already all for weak gravity. So this is a weak gravity Lagrangian finally. 1, 2, 3, 4 torsion square pieces, one of which is parity violating, all the others are parity conserving. And if you have vanishing torsion, you cannot have any parity violating piece. Parity violation in weak gravity is only possible with torsion. This piece vanishes about zero immediately if torsion vanishes. And if torsion vanishes, obviously these pieces are absent. So if you want to couple antimatter in a different way to weak gravity, in a parity odd form, you are required to introduce torsion. This is a good argument in favor of torsion or against torsion, depending on whether you find or do not find such couplings to antimatter. Minus, and now we have the strong gravity piece, and I hope you have now understood how it comes about. Now we have here the torsion. Of course, now we have all the quadratic pieces in curvature. And we order them in a way which perhaps is W6, which is a curvature scalar, of course, over 12, times R squared, which is just the curvature scalar and square, minus W3, so of course the pseudoscalar as we know, over 12, times the pseudoscalar x squared. Okay, and then quite obviously we can have a mixed piece, which is plus mu3 over 12 times r times x. So these are the simplest curvature square pieces. This is, for instance, one piece which Yang used in his gravitational theory, but he had no weak pieces, he had only a strong piece. And so he didn't have conventional gravity as a limit. And then we have different pieces. This is now the scalar and pseudoscalar. Now we come to the rich symmetry plus W4 times rich symmetry is number 4 of curvature R alpha beta rich hot star of 4 R alpha beta. This is already, and now we have a couple of pieces which only appear in spaces with torsion. If you have no torsion, of course, this piece vanishes, but this piece, which Yang used, is there, and this piece is there. And now you have pieces which only appear in spaces with torsion, plus R2, which is the pair form, R alpha beta, H, and now parentheses, we have W2, of course, is a pair form, H star of 2 of R alpha beta plus U2 times R4, these are 4 alpha beta. And now we get only 2 more pieces. Now you can relax already. R5, which is the anti-symmetric piece of the Ricci, alpha beta Rich W5 times R alpha beta plus mu4 times the 5th piece, which anti R alpha beta. That's already all. Okay? These are the strong gravity pieces. So that's the complete Lagrangian. And let me just make a remark. So for for instance, the Sciama-Nestor, which was our starting point really, and only then we were courageous enough to develop the whole Lagrangian, because we saw that it's necessary to have these parity violating pieces if one wants to make consistently. So which really induced, I have to say, I mean, induced me at least to reconsider all this. Sciama-Nestor and Yo here, I think Hehl went to industry as far as I know, so he's no longer. And Sciama-Nestor is presently in Beijing. So the Sciama-Nestor Yo was this piece, then the vector piece, this piece, and this piece. Wait a minute. This piece. This was the Sciama-Nestor Yo Lagrangian, and then it generalized, and then we made a little bit more different, a more general Lagrangian, which I'm now lining out. But I want to underline what did we do here. We just have the status of Young-Mills theory of 1954. What we have is in principle the field equations, which I wrote down there, and we have what is the analog of the Young-Mills Lagrangian f wedge star f. This is the analog of the Young-Mills Lagrangian f wedge star f. I mean, if you analyze it, and I hope I have shown to you how we did it successively, we started from the known Einstein theory and coupling constant kappa, and we generalized to torsion square pieces and teleparallelism, so we are in known territory. But then, since we have to add curvature square pieces, if we want a decent gauge theory, we want to propagate the connection. This propagates only the tetrad, the coframe, and this propagates the connection. We have a new field. We speculate that there is a new field related to the Poincaré group, which is the field belonging to this variable, the connection. So the connection now propagates, and we have typically wave theories for connection. We have new excitations. So this is the Young-Mills Lagrangian of 54, and this is our answer to gauging the Poincaré group. This is the corresponding piece to Young-Mills theory of 1954. We have recovered a known interaction, and we speculated on a new interaction. And in order to make physics, of course, we have to find out whether this new interaction makes sense, whether it exists in nature or not. But there are encouraging signs insofar as, for instance, these very, I say it now naive, relatively naive models already give an accelerating universe. And this is not ad hoc, but this you can just derive from making a Friedman ansatz and looking for expanding universes, and you find accelerating terms which, as far as we understand, are induced by torsion square pieces and which effectively change the cosmological constant. So there are signs that such models may have something to do with reality. We still don't know, and we are open for new developments, and I hope you got an idea why we think that such an approach is very much in the spirit of what we learned from Young-Mills and company, Utiyama, Sciama-Kibble, that this is the consequence of all these ideas and what has now to look into a selection of, I didn't now count the arguments. The unknown constants are about, I forget now, you can count yourself, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14 defined, I mean, apart from the Hopking constants, this is known, this is unknown. We have 14 defined, we miscount 14 parameters which we can adapt. And perhaps by looking for propagating modes, one can exclude a lot of parameters and can narrow it down to a theory which makes early predictions. But this is open, and I don't know the answer. Thank you very much for your time.
This is the last chance for the questions. End of the talk. Anybody have further questions?
I want to check the A1 term is even parity or odd parity.
This is
This
this is even parity. Oh, there is a one. There is a one. I'm sorry. This is just tensor p's. This is one and the Hodge star one. It's Hodge star one T alpha. T one alpha which. So that was a misprint. This is a this